Okay, hi everyone. My name is Guillaume. I'm a PhD student at EPFL, and I'm going to talk to you today about Dotty and IDE and related cool stuff. So what's Dotty? So it's this cool new compiler we've been working on, which will eventually become Scala free, hopefully, which has this redesigned type system internals, but that really looks very similar from a user perspective. And if you want more information, we have a website and we have some blog posts on the official Scala website which shed more light on this that you should take a look at. But Dotty is also a chance to redesign some of the components of the compiler just because we get to do things again, so with the benefit of hindsight, we can do them better sometimes, hopefully. One of them is incremental compilation, which is slightly better in Dotty in that we avoid under compilation, that is not forgetting to compile stuff that has changed, say when you use final val, which is one thing which might be fixed in Scala C2 at some point. We also have better pattern matching checks, which have been adopted into Swift actually, which tells you how good they are. And of course, it's also a chance to redo tooling, because so if we want developer to use our thing, we need to have good tools. So we have a REPL, which even has syntax highlighting, thanks to Howie's Ammonite library. We have DottyDoc, which we use to generate the documentation for the whole website. And we have IDE support, which is what I'm going to talk about today. So before talking about what we're doing, let's review like what's happening in the world of Scala. So basically, there's two kinds of IDEs that are widely used today. There are those based on the Scala presentation compiler, like the Scala IDE Eclipse plugin, and there's Enzyme. And then there's another kind of IDE which re-implement the whole Scala type checker from scratch, and that's basically the Scala plugin for IntelliJ. So all those projects do interesting things, but we can't really reuse them directly with a new compiler, especially since there are usually like quite a lot of lines of code. Enzyme is the most interesting one here because it has this server client design, which means some parts could eventually be reused. But I'll talk more about that kind of things later on. Okay, so what are we trying to do here? So if we don't want to fall into the same trap we fell in before with like the Scala IDE, where we became forced to, like, we became trapped with Eclipse, we need something more general. So the principles we're after are like code reuse. As much as possible, we don't want the IDE to have code which is custom to it and not reused by the compiler. We want to be editor agnostic, not tied to Eclipse or IntelliJ or anything like that. And of course, we want it to be easy to use and to install. So let's go through these principles one by one. So code reuse. So to understand that, we need to understand a bit how the compiler works. So there's a bunch of things going on in the compiler. This is like an abstract view of the compiler pipeline. It does a bunch of things, which basically the way you can understand it is we start with your source code, you parse it, you get untyped trees, you type check it, and then everything else until you get to the backend is just progressively simplifying trees until you get to something that can be emitted as JVM bytecode or can be used by Scala.js or Scala native. So given this, like, how do you get information out of the compiler to use in an IDE? So basically, you need to figure out which tree you want to query and how you're going to do it. So as an example, suppose that I have this code, like I have a final val, and I have another val that refers to this final val, and this little flag is where the user put his cursor position. And I want to do a jump to definition. So after type checking, this is what the trees look like. And so every tree node has a type and a position, which means that I have all the information I need to answer the query. I can just traverse the trees, starting from the user position, to find the tree definition, which corresponds to the symbol where the user has put his cursor. So we can answer the query. But if we go a bit later in the compiler pipeline, then we can't answer this query anymore because we've lost information because of constant folding. And it's just impossible to answer the query. So it's very important that to query the compiler, we need to start trees before any of the late compilation transformation phase. And we can then respond to the ID queries by traversing those trees. But then that raises a question, like, what do you do about code that has already been compiled? So by this, I mean, when you're in your IDE, usually you have a few files which are open, and then everything else is not open, is pre-compiled, and is the rest of your project that you're not working on currently. But you still want to be able to go to definition or find references in files that are not open in your IDE. To understand that, I'm going to talk a bit about pickling. So pickling is a very early compiler phase, which basically stores information about the type check trees, which will be stored at the end in the class file that we generate. In Scala 2, this is used to store method signatures, and this is useful for separate compilation. Because if I have a.scala and b.scala, once I have compiled a.scala to a class file, and I try to compile b.scala that uses a.scala, I need the Scala signatures of all the methods in A to be able to use A. I cannot rely on the JVM level bytecode signatures because the JVM doesn't know about all the Scala types, and in particular, it doesn't know about type parameters at all. So in Dotty, we also have a pickler, but it goes further. It stores the whole trees of the type checker output. We call this tasty because pickers are tasty. It's the typed AST serialization format. And the main motivation for doing that, the original motivation, is to solve the binary compatibility problem. Briefly, if we always use JVM bytecode, then if there's compiler encoding changes, like between Scala 2.11 and 2.12, they change how trait methods are encoded, which means that it's impossible to reuse 2.11 code as a dependency of 2.12 code. So binary compatibility was broken. So an alternative can be source compatibility, which is something that some build tools are now exploring. But an issue with source compatibility is that if the type checker changes, if the type inference algorithm or the way we do implicit search changes, then your source code might not recompile anymore. So it's not perfect for compatibility either. So Tasty is sort of an alternative that sits between the source code level and the bytecode level, where we recompile starting from the type checker output. So the type checker output is a much higher level than JVM bytecode, so it doesn't contain some encoding details that can be binary incompatible, but at the same time, Tasty output is after we have done overloading resolution and type inference and implicit search and all of those things. So that kind of details does not influence how the compatibility of Tasty. But we don't care about this in this talk. We only care about IDEs. So what does this have to do with IDEs? Well, the interesting thing is, once we have these trees, then we can just like deserialize them on demand and query them in the exact same way we queried trees from what the user was typing to be able to answer features. So to do this, we've implemented some interactive APIs on top of the compiler that like basically have just some convenience methods for doing tree traversals, compiler lifecycle management. We use them both in the IDE and the REPL. And in the future, we intend to use them for more stuff, like being able to do interruption handling or partial type checking. Say, every time you press a keystroke, you don't want to fully recompile the current file. You could just recompile the subset that you need to get errors for the current method, that kind of things. And the interesting thing is that all of this is basically less than 1,000 lines of code. It's not complete, but it already does a bunch of things for you. Okay, so editor agnosticity. So if you've been to Olaf talk yesterday, this should be familiar, because this is exactly the same thing I'm going to say again. Basically, you have this IDE portability problem of, well, I have M IDEs, I need to support N programming languages, I need N times M IDE plugins. And this is especially bad because to be able to write these IDE plugins, you need to be an IDE expert and you need to be a compiler expert. And usually those are set of people that don't really intersect. So the language server protocol is an attempt at solving this. And the way it works is you basically have a tool on one side, which is usually a compiler, an IDE, sorry, and the language server on the other side, which is usually a compiler. And every time you do something like open a document or edit a document, you send messages from the IDE to the compiler, and then the compiler can respond with its own messages, or can even like ask the IDE to do things like rename definitions in all these files. It's been first implemented in VS Code. It uses JSON RPC. I just talked about how the notification stuff works. An important thing is that it's completely asynchronous and cancelable. So you should never get your IDE to freeze because your compiler is busy type checking. So that's built into the protocol. So how do we make a language server for Dotty? Well, it's actually pretty easy because you have libraries that do most of the low-level stuff for you. In Dotty, the Dotty language server, we use ASP4J, which is a Java library. There are Scala libraries to do this now, but we can't really use a Scala library inside a Scala compiler because you get into bootstrapping issues. It relies on the interactive APIs I just talked about, which means that in the end it's very small. So just to go show that there's really not much magic here, here's how you implement the definition method. So it's provided by the ASP4J framework, and it takes as argument the parameters of definition, which is the position of the user cursor, and the answer you want to get is all the definitions that correspond to this method. So you want overridden definition too, usually. So you're going to do an asynchronous computation, which takes a cancellation token that can be used to interrupt. So basically, the user asks for the computation to be interrupted. Then you can check this cancellation token to see if it's been interrupted. So first you get which file does this query comes from. Then you get a compiler instance that is responsible for handling this file in the IDE. Then you get a compiler context to do a computation in the compiler. Then you translate from the LSP representation of position to the Dotty representation of position. Then you look into your open trees to find the AST for the current file. You traverse this tree to find the symbol at the current position, that is the position the user was at when he pressed go to definition. From this position, you can get the tree where the position exists, and then you can just traverse this tree to find all the position of all the definitions that correspond to this symbol. And then you will just map that back to something that ASP4J understands. So there's lots of going back and forth between different representation of things, but there's nothing really magic about it. Last design principle, and the most important one, you want things to be easy to use, of course. But it's not really easy, is it, with SBT or any build tool, really. So the kind of things we want to do is basically analyze the build, find all the Dotty projects, compile these projects, generate configuration files for this project, install the VS Code extension, assuming you're using VS Code, and then launch the IDE. So we do that by generating two configuration files, one which just has the current version of the Dotty language server for this project, and another which has things like, for each of your sub-project, what's the compiler version, what flags do I need to pass to the compiler, what are the source directories, what's my class path, where are my output classes. So this is all very boring and tedious to do, and you'd have to redo it for every build tool. So in the future, we hope that instead of doing that, we can just ask the build tool, like, give me this information online and not have to store it in a file that might become out of date. So this is what the build server protocol hopefully will achieve. But that's not enough. We also need a discovery protocol of some sort, because if you're just starting in a project, like, you need to know, how do I start the build server for this project so that I can then query it for things. So that's another thing that hopefully we'll get soon, but that doesn't exist yet. To revisit the principle I just outlined, we want code reuse. We achieve that by basically having APIs built into the compiler for interactive usage. And most of they're like a thin layer on top of the compiler itself. We want editor agnosticity, so we implement the LSP, and we want things to be easy to use, so we have an SBT plugin, which you need to use Dotty anyway, and one command, launch IDE, that just starts everything for you. But we can do better. We want 0 commands. Okay, and now I want to raise the bar compared to Olaf's talk yesterday, and because people always want more features, of course. What about debugger support? That's important, right? So it turns out that there's another protocol for that, which is called I don't know what it's called. It's specific to VS Code, I think, because no one but VS Code implements it. It's based on the Chrome debug protocol. And there's a Java Debug Server that implements it, and which is very, very powerful and complete. And it turns out that Scala runs on the JVM, and you can just use the exact same things to debug Scala than Java, because the JDI is pretty low level, the Java debugging interface APIs. So most things just work if you make a Dotty Debug Server that calls the Java Debug Server. It's actually not actually merged in Dotty yet, so we'll see how that actually goes. But one especially changing part is expression evaluation. So when I talk about expression evaluation, I mean here's some code. You put a breakpoint here. So now this means breakpoint and not cursor position anymore. And then at this point, you want to evaluate foo in your debugger. So how do you do that? Because you have a running JVM somewhere, and then you're in your IDE, and you type foo, and somehow you need to be able to call that on the remote JVM. If foo was just a regular method, then that'd be easy. You can just use the Java debugging APIs to do a remote call. But here, you need to actually do type checking. Here you need to do implicit resolution, among other things. So how do we do that? If you look at like what IntelliJ or the Scala IDE does, the answer is you write thousands and thousands of lines of code to try to imitate what the compiler does. But I think we can do better than that. I think we can just run the full compiler pipeline. So we just insert this thing in the source code at this position, and then we run the compiler pipeline, and it's going to do implicit resolution and everything for us. At this point, we can't really do anything with this because this is in some non-static method, we have this code that we want to evaluate. So we need to extract the expression that we want to evaluate on the remote VM to a static method. And all the parameters of that are used in this expression need to become parameters of a static method. And then we need to make things a bit even higher level, because on the remote VM, we don't have variable names. We know that we have something which is a self, which is the current this type in the stack frame, and then we have a map of local variables. So we need to, basically, to do this, we have a compiler phase that does all this extraction phase stuff. But then we're still on our local JVM, trying to debug a remote JVM. And so we've compiled this thing down to a class file, but now we somehow have to send this over to the remote JVM, like inject a class file in the remote JVM. So what do you do? Basically, you want to be, and then once you've loaded it, you need to call the static method with the right arguments. So we can cheat a bit and add some kind of hook in the standard library of Dotty to be able to do this. This isn't actually necessary, but it makes things a bit easier. And the only thing this thing is going to do is take a class path and take the self and the list of local variables you get from the Java debugging APIs, and then do a call to a method after doing class loading. So on the debugging VM, the one that is going to call the debugged VM, this is the schema of the stuff we want to do. Like, we're going to get a class path for the global class we just created. We're going to get the self variable, the list of local variables, and then we're going to do a magic remote call. And the JDI APIs are absolutely horrible, but this is completely possible. So if you do all of that, and so this is VS Code, and I'm going to go to the debug pane. Say you have some simple code here. I have some object with a variable x whose type is any, and I'm kind of curious of, well, how does compilation of this thing work? Well, I can use my compiler to compile my compiler and then debug my compiler with my compiler. And so if you look into it a bit, you'll understand that what's going to happen is that 42 can't really be stored in a variable of type any without boxing. Like, it has to become an integer. Boxing is handled by a method called box in erasure. So we can put a breakpoint at the top of this method. I hope you can see something. And then we can start the debugger. And here we already get a lot of things for free thanks to the Java Debug Server. So here we have a list of local variables, and you can drill down into them and see the fields of this local, of all the local variables. And it even does cool things, like if I hover over something, I can get the content of this thing at runtime. But we are interested into expression evaluation. So I'm trying to see what this box method is doing. So it's taking a tree. So let's look at what this tree is. Okay, so it's a some kind of literal, but that doesn't really tell me much. So what I can do is print that thing. Okay, so it's literal of constant of 42 is the tree. Let's print its type. So it's the type, the row type is these complicated things. But it's probably int, but to show that properly, I should do pretty printing. So we have a method to do pretty printing, it's called show. But show takes an implicit context argument, so I really should be doing like show of context, given some context. But hey, I can just let the compiler do that for me. Hey, so it's int. So did you see what happened here? I just did implicit resolution at runtime, because we didn't have enough problems with implicits yet. So let's step through things a bit. Let's go. Let's see what this method does. So are we going in this case? No, we're going in this case. Then there's a bunch of things we check. We get into this branch. Okay, we are at the end of the method. Is arg empty? Yes, so we're probably going to do this stuff. So what the hell does this do? So what's class? It's some kind of symbol. I could look into all of its field, but that's not really useful. I can just do print it instead. So it's just int. Ooh, I scrolled down a bit. Okay, so what does box method of class as class does? It returns a method called box. And turns out in the object int, there's a method called box. Did you know that? We can create here now. Yes, it's an integer whose value is 32. Right, so what does ref of box method of class as class do? It returns some kind of tree. Interesting. What's this tree? Well, of course, it's going to be the tree that corresponds to the method. And then we can probably guess what this is going to do applied to tree. But let's check anyway. Yeah, so the tree we're going to return from this box method is a call to scala.in.box of 42. So now we understand what box is doing. Yeah. Okay, so future work. Optimizations, of course. As I said, the IDE doesn't do enough optimizations yet, in the sense that every keystroke we're going to retype check the full file, which is actually pretty fast most of the time, but we can be faster. More features, we always want more features. A big one is basically documentation and hover, which means we want to store in Tasty the content of the documentation of each method. And if we do that, then not only do we get documentation in the IDE, we basically can reuse it in the REPL too. We could have a :doc command in the REPL to get documentation. I think that'd be very cool. Better build tool integration with the build server protocol, and probably more stuff. So to conclude, you should design your compiler with interactivity in mind, because it's kind of important nowadays. And you should also design your build tool with interactivity in mind, because that's also important. And I think we should try, now that we have tools such as the language server protocol that help take care of the low-level details, we can do a much better job with IDEs, and we can go further than what existing tooling has been doing. In particular, I'm very excited about the kind of things that Idris is doing. So there's this book called Type-Driven Development with Idris, which kind of sketches out the things that could be possible in other languages if we just take care of our tooling situation. Thank you very much. Questions? Yes?
Maybe my one slight disappointment with that, which isn't your fault, is that breakpoints appear to be line-based.
Oh.
To get more precise,
So the question is, are breakpoints line-based? So in the VS Code protocol, breakpoints don't have to be line-based. They can be colon-based. The difficulty with this is the JVM, by default, only stores information about lines. For each bytecode instruction, you know at which line it is. But we can do better than this just by knowing in what class we are in the current line, because in Scala, if you have like deeply nested code, you can have multiple classes on the same line, and you can just check that to be able to do things a bit more precisely. I think we can do even better than that if we store more debugging information in the JVM. So there's a JSR, a Java basically a Java feature that has been implemented, which is about providing more debug information in the class files. And I think if we implement that in the backend of Scala C and of Dotty, we can get colon-level information. And I think there's a Scala Center proposal for this was approved a while ago. So that might be coming, hopefully. All right, thank you.